Oh, hello everyone. In this video, we will revise the electromagnetism topic of Year 12 physics. So first of all, we will look at the magnetic field of a current carrying wire, then the force on a current carrying wire, or basically how does a motor work, and then the force on a charge in a magnetic field, and then finally what is electromagnetic induction. So let's get started. There is a current carrying wire. There will be magnetic field around it. And that magnetic field gets weaker when one moves away from the current carrying wire. And magnetic field will be stronger if current is increased. So by looking at this one, this equation, B stands for magnetic field, unit is Tesla, it's directly proportional to the current, inversely proportional to the distance. Mu naught is a constant and 2 pi is a constant. So that formula can be used to find the size of the electric field around a current carrying wire. And to find the direction, we use what is called as the right-hand grip rule. So if you hold the current carrying wire, if you imagine you're holding the current carrying wire, so your thumb is pointing in the direction of the current, then your fingers will curl in the direction of the magnetic field. So like, for example, this is the current is coming out of the page, fingers are curling this way, which is the clockwise direction. Now, that was the electric field. The main focus this year is on the motor effect, which is basically how does a current carrying wire experience a force when it is placed in a magnetic field. So there are two magnets. So their lines of magnetic field always go from north to south. So if there is a current carrying wire placed in a magnetic field, it will experience a force and it will move. You might have seen that demo in the classroom. Now, how do we find the size of this force on this current carrying wire? That is equal to, is directly proportional to magnetic field. If magnetic field is stronger, force will be stronger. It depends on the size of the current and it depends on the length which is inside the magnetic field. Now, why does the wire experience a force? Because this current carrying wire will have a magnetic field around it. And that's the magnetic field of the magnet. So these two magnetic fields of the current carrying wire and the magnets, they interact, attracting or repelling and making the wire move. So that's the reason. Now, if there is a 90 degrees angle between the direction of the current and magnetic field, then force will be maximum. And if this wire is parallel in the same direction as the magnetic field due to the magnet, then there will be no force. Or in other words, sin theta is involved. So that's the formula. How do we find the direction? We use what's called as right-hand slap rule. So what you imagine is that you place your hand in such a way that your thumb is pointing in the direction of the current. This one is pointing in the direction of, fingers are pointing in the direction of the magnetic field. Then direction in which your palm will move to give someone a slap will be the direction of the force. Remember, all these three are at 90 degrees angle. So say, for example, if we apply this rule to this diagram, so imagine you're holding your right hand in the direction of that red arrow, and your fingers are going from north to south. If you do that, and then a slab is coming towards you, or in other words, that this one will be, this wire will be experiencing a force in an upward direction. Okay. If direction of this current is reversed, then the direction of the force will be reversed. So that's the basic principle for the force on a current carrying wire. How do we make use of that one is in electric motors, and that's why it's called the motor effect. So instead of a single wire, there's is a coil of wire which is placed in the magnetic field. In real life, there will be many, many coils. So say, for example, current is going from D to C, B, and lines of magnetic field are going from north to south, so that will be to the right. Now, if you look over here and the side DC, then using the right-hand slap rule, the force, you put your thumb over here in this direction, magnetic field is from north to south, and using that, force comes downwards. So this wire, this side of the coil will be experiencing a downward force. This side of the coil AB, where current is going from B to A, force is upwards. Now, this coil can move about the central axis. Now, if we look over here, current is going from C to B. Lines of magnetic field are in that direction, so they are parallel. So no force will be experienced by side BC or side AD. These part will not be experiencing any force. So these one will be experiencing the force only. Now, if the force is in this direction, and that's the distance from here to there, from the axis of rotation up to there, that distance from here to there, so it will produce a torque or a turning effect. So force time that distance will be the torque, or in other words, this coil will move in a clockwise direction as shown by these arrows. Now, in a real motor, there will be many, many loops. If there are 10 loops, then torque will be, so magnetic force is BIL, and because there were two sides, the total force will be 2 times B times by L. And if there are n number of turns, then there will be, we will have to multiply it by n. In real motor, there will be commutators and brush. You can watch a little bit of video over here to show you how does actually a DC motor works, but these are the basics of the DC motor. Now, let's move on to the force on a moving charge. So here, now, in a conventional current, we say that positive charges are moving, whereas positive charges actually don't move in a wire, but that's what a conventional current, it goes from the positive towards the negative for battery. So if in a wire, there are charges which are moving and making the wire experience a force. So if there are loose charges, positive or negative, and when they're moving through the magnetic field, they will experience a force. Let's figure out what direction will that force be first. So there's a positive charge here. It's entering at a certain velocity. Now, if we apply now right-hand slap rule by applying your thumb in the direction of the motion, that's to the right of the page in this direction, place your thumb in that direction. Magnetic field crosses mean magnetic field is into the page. And that gives you force and upward direction. So this positive charge will experience the force in an upward direction. And whenever there is a force which is at 90 degrees angle to the velocity, it does not change the increase or decrease the speed. It actually makes it move in a circular path. So this charge will actually move in a circular path like this one. Now, negative charge, if there is a negative charge which is moving upwards, again, we apply right-hand rule, but remember your thumb will be in an opposite direction to how the electron is moving. So point your thumb down the page, lines of magnetic field, so your fingers should be into the page, and your hand moves to the right, so force on this one will be to the right. So I will show you here. So this positive charge experiences a force in that direction, so it will go in a circular path of certain radius, but we will figure out in a minute. This charge will go in a circular path because it was experiencing a force in that direction, so it will move in a circular path like that one. What's the size of the force? Size of the force depends on B, Magnetic field, Q is the charge on the charged object, and V is the speed. Remember, capital V is the voltage, little v is the speed. So that's the magnetic force. And remember, an electron moves in an opposite direction to the conventional current or a positive charge. We already talked about this right-hand slap rule that we use to calculate the direction of the force. Now, so we know that size of this force is BQV from here. And this is the centripetal force, and centripetal force is always equal to mv square over r. So by equating this one, BQV equals mv square over r. If we are given the speed, we can calculate the radius, or if we were given the radius, we can calculate the speed. So that was the force on a charged particle when it's moving. Remember, if the speed is 0, if the charge is not moving, then it will not experience any force. Now, last thing in this one is electromagnetic induction. Now, electromagnetic induction is opposite to the motor effect. In motor effect, what we have is that the current and magnetic field together, they produce motion. In generator effect, electromagnetic induction is how current is produced, and current is only produced if there's a potential difference or a voltage. So therefore, it's called a generator effect. So if there is a motion or a force, and there's a magnetic field, then it will create a current. And because it doesn't come from a battery, it will be called an induced current or induced voltage. So let's look at first of all, the size of this voltage. So over here, there's a rod AB. It's made up of some conducting material like copper. It's moved like down the page, like that one. As it cuts the lines of magnetic field, the electrons which are there around the atoms in the conducting material, they experience a force and they move. And if they move, they move either towards A or B. So there will, if they have moved, that means current has been produced or a voltage has been produced. Now that size of that induced voltage is proportional to so induced voltage will be larger if magnetic field is stronger. If the speed of a movement is faster, then there will be bigger voltage, and it also depends on the length. How much length is there inside the magnetic field? So only this part, which is where lines of magnetic field are cutting the moving electrons, only that length will be included in this calculation. So formula is BVL, and maximum voltage if V and magnetic field, they're at 90 degrees angle, and 0 if they are parallel. Now, so what it means is, so if there's a voltage induced, we can calculate the voltage, then current will be V induced divided by resistance. So how do we find the direction of the induced current or the voltage? We use right-hand generator rule. So what you know are your fingers and your thumb. So we will, and your direction in which your slap will move, or you can put your middle finger out. That will be the direction of the induced voltage. EMF means the same thing, voltage. So applying here. So if you now take your right hand, place your thumb down the page, your fingers should be in a direction of the magnetic field. That means from B to north to south. So that's where they are. And if you move your arm, right hand, that means that is from B to A. And that is the conventional current. So that means charges, positive charges will move, or current will flow in this direction. Now, over here, it's not a complete circuit. So what will happen is, in actual practice, positive charges don't move, it's the electrons which move. So if that's the direction of the induced current, that means electrons have moved in the opposite direction. So this one has become negative, and B has become negative, and A has become positive. So if we connect a resistor over here, what it means is that this is a positive current will come out from there, and it will make, so if it's a complete circuit, current will keep flowing as long as there is the movement in this one. So that's the basic principle of electromagnetic induction. So thank you for watching this video, and that's all for